Good day everyone, I am Christine Kayla Mascado from BSEC 3A. So today, I will be presenting my analysis on the Sawtooth signal covering everything from Fourier series derivation to simulation. Here is the overview of my presentation. We will start with the introduction and mathematical definition, followed by the derivation of the three Fourier series forms, afterward computing the RMS voltage, validating using MathCAD, and showing the circuit implementation. Let's define the wave first. A sawtooth wave is a periodic waveform named after its shape resembling the teeth of a saw. It has a linear ramp-like rise followed by a sharp drop. Distinct siya because unlike a square wave, it contains both odd and even harmonics. So mathematically, for one period from 0 to t sub o, the signal is defined as a straight line starting from the origin. So the equation is simply x of t is equal to a over t sub o times t. So here, a is the peak amplitude and t sub o is the period. So basically, formula lang ito ng slope. Now let's proceed to the core of the analysis, the Fourier series. We will derive it in three forms: exponential, trigonometric, and combined trigonometric. First, the exponential form. Start muna tayo sa C sub O or the DC component. To find the C sub O, we calculate the average value, so we integrate the function of t over one period. Since calculation ito ng area ng triangle, the result of the integration is simply A over 2. So our average voltage is half the peak amplitude. Next, we solve for the coefficient C sub k. The formula requires multiplying our function t by a complex exponential e raised to negative jk omega sub ot. Since multiplication ito ng variable t and an exponential, we must use IBP or the integration by parts. So we let u is equal to t and dv is equal to e raised to negative jk omega o sub ot. So substituting this into the uv minus integral of v du formula, we get the expansion of this. Applying the Euler's formula, alam natin na ang e raised to j 2 pi k is always equal to 1 because it represents a full rotation. So this simplifies our equation significantly. After canceling out terms, the final expression for our coefficient is c sub k is equal to j a over 2 pi k. Now for the trigonometric form, a sub o is the same as c sub o. So it remains a over 2. And then yung a sub k, the cosine coefficients, so when we integrate for the cosine terms, the result is 0. So this tells us that the AC part of the wave relies on sine terms. Then the b sub k, sine coefficients. So for the sine terms or b sub k, we perform integration again. After evaluating the limits from 0 to t sub o and simplifying using the fact that cos 2 pi is equal to 1, we arrive at the final coefficient na a over pi k. So finally, the combined trigonometric form, here combining the real and imaginary parts. So we combine yung real and the imaginary parts. Since pure imaginary ang calculation natin kanina, yung c sub k has like j, the phase angle theta k sub k is 90 degrees or pi over 2. So the magnitude is derived using the Pythagorean concept, resulting in a over pi k. Moving on to the voltage analysis, let's find the root mean square or RMS value. So the process is in the name itself, square mean then root. First, we square our function to get a squared over t sub o squared times t squared. Mean, we integrate t squared, which gives us t cubed over 3. Evaluating this 0 to 2 to t sub o, we get a squared over 3. And for the root, we take their square root. So the RMS voltage of a sawtooth wave is simply the amplitude divided by the square root of 3. To verify if our derivations are correct, I used MATCAD. I defined the parameters with amplitude is equal to 10 and period is equal to 2. As you can see in the plots for exponential, trigonometric, and combined forms, the resulting graph creates a perfect sawtooth wave. So this confirms that our derived formulas are correct. For the practical application, I simulated a circuit. So the circuit uses a capacitor that charges linearly through a resistor, creating the ramp up, and discharges quickly through a transistor, creating the drop. So the oscilloscope output confirms the behavior, a linear rise and a sharp drop, consistent with our theoretical sawtooth wave. Before we conclude, it is crucial to understand how we can manipulate this waveform. In signal processing, we use 6 fundamental transformations to analyze how a signal changes under different conditions. So we divided this into categories. So time domain and amplitude domain. So first, let's look at the time domain. So these transformations affect the when and how fast of our signal, altering the horizontal axis. Transformation number 1 is time shifting. This is where we shift the signal left or right. In a circuit, this represents a time delay. For a sawtooth wave, shifting, it changes the phase angle in the Fourier series. Number 2 is time scaling. This compresses or expands the signal. If we compress it, the signal speeds up, effectively increasing its frequency. If we expand it, it slows down. Number 3 is time reversal. This flips the signal across the vertical axis. It essentially playing the signal backward in time. Next, we have the amplitude domain. These transformations affect the strength or intensity of the signal, altering the vertical axis. Transformation number 4 is amplitude shifting. We move the signal up or down mathematically. This adds a DC component or offset, directly changing the average value of the wave. Number 5 is amplitude scaling. This stretches or shrinks the height of the wave. In electronics, we call this amplification or attenuation. It scales all our Fourier coefficients by a specific factor. And finally, number 6 is amplitude reversal. This flips the signal upside down. It is equivalent to multiplying by -1, representing a 180 degrees phase shift. So by mastering these 6 transformations, we can predict exactly how our sawtooth waveform will behave when passed through different filters and systems. And yes, this brings us to the end of our analysis. So through this video, we've seen how the Fourier series isn't just a theoretical concept, but a powerful tool that connects math, software, simulation, and real-world electronics. So yes, thank you for listening to this presentation, and I hope you found it informative. Goodbye and thank you for watching.